This is the second video for the Microfluidics device. We'll be picking up where the last video left off, which is we've just completed our geometry and mesh, and we're going to go ahead and run Fluent. So we're going to be using the double precision again, and on VMware I'm going to go ahead and use 4 processors. So we're going to be performing what's called a multi-phase simulation. In particular, we'll have 2 phases, one oil and one water, and go ahead and look at the generation of oil droplets within this microfluidics device. So we're loading up the mesh. And there's our mesh. Okay, we are going to be running a transient simulation. And before we set our models, we're actually going to go ahead and create the 2 materials that we're going to be using throughout the simulation, which is the oil and water. Okay, so let's open up our material, fluid, new. We're going to, for our water, we're going to load our Fluent database, scroll to the very bottom, and you'll see water, liquid. It's got its properties in here, and we'll copy this into our domain. And then we'll edit our fluid 2, or fluid 1, and we'll call this fluid oil. We'll set our density to 1000 and our viscosity to 0.006. Create and close. So now we have our 2 phases. Our main phase, our primary phase will be water. Our secondary phase will be oil. So let's go ahead and take a look again at our model. So we're going to first set our viscosity. We're going to be operating in a very low Reynolds number flow, so we can convert our viscosity to laminar. And we're going to go ahead and turn our multi-phase flow on. So we have a couple different ways of modeling the different phases in the system. And the process we're going to use is what's called volume of fluid. And effectively what this does is it creates a new variable, a new field variable, which represents the volume fraction of phase 2 relative to phase 1. So for instance, if we have a cell filled with oil only, the volume fraction of that phase 2 in that cell would be 100% or 1. If we had a cell that was filled exclusively with water, the volume fraction in that cell would be 0 or 0%. And so that variable alpha is going to be changing across the field, and the 1s and 0s are going to be moving corresponding with the droplets or the water moving throughout our domain. Okay? So we're going to go ahead and do an implicit implementation. We'll talk about that in a couple of weeks. And we will sharpen our interface. So the interface between an oil droplet and a water bath is infinitesimally thick. There's basically a very thin interface between oil and water. And in the model, in the simulation, that thickness is going to be reflected by a number of cells. And so obviously we're not going to be able to get that infinitesimal thickness interface. And so what we're going to do is we're going to be using different models within Ansys to try to keep that interface as thin as possible. Okay? Within the phases, we have to apply first. For the phases, we're going to set our primary phase, phase 1, that's going to be our water. And phase 2, that's going to be our oil. And we're going to apply on both of those and just confirm that phase 1 is the water, phase 2 is oil. Okay. Next, we're going to talk about phase interaction. So this is the different forces at play. And so we are going to turn our surface tension on. We're going to set our constant value of 0.005. This could potentially change with temperature if you wanted, but we're not going to do that. And we are going to turn on our forces, our surface tension forces, and in particular wall adhesion, so the particle or the droplets are allowed to adhere to the wall if that's what happens in the model. Okay, we're going to apply on all of these things and go ahead and close. So that sets our model. We've already set our materials. Cell zones, this will be set as the mixture. So you can see our phase is a mixture of the two. So we don't have to specify in particular one or the other. We will initialize the system in a little bit, filling it with water. So let's take a look at our boundary conditions. We have two types of inlets, our oil inlet and our water inlet. For our oil inlet, we're going to turn our phase 2 volume fraction to 1, meaning that our oil inlet is 100% phase 2, which is our oil. So okay on that. Let's go ahead and set our velocity for the inlet to be 0.01 meters per second. Okay. For our water inlet, we don't need to change the phase 2 volume fraction because it's going to just be water, which means it's going to be 0% oil. But we do need to set our velocity, which will be, again, 0.01. Okay. Nothing needs to be done for our outlet, but we do need to focus on our walls. We are going to have no slip boundary conditions, so stationary wall, no slips, so that all looks fine. The key change that we need to make is our contact angle, and we're going to set this value to 135. Okay. So that sets our boundary conditions and finishes our setup of the problem. For our monitors, we're going to set all of our residuals to be 0.0001, so 10 to the minus 4. So we're all good on that. For initialization, we're going to have a couple options. So we're going to do standard initialization, set all of our values to 0, including our phase 2 volume fraction, which means our system will be filled initially with water. We can initialize. And go ahead and at this point we can produce a contour of our volume fraction. And so if we want the volume fraction of oil, that would be our phase 2. And we can save and display. So we can see, oh, where'd it go? Try that again. Our phase 2 volume fraction, there we go. And we can zoom in a little bit so we can see everything is a value of 0, which means everything is filled with water except for our inlet, which is a value of 1. Okay, we'll call this contour oil. Okay, we'll turn on a solution animation, which will animate our oil profile using the active view every time step. Okay. Then we can go ahead and run our calculation. We're going to take, for the homework, we're going to end up taking 200 time steps each of a value of 0.001. Maximum number of iterations we'll set to 50. Reporting interval we'll set to 25. And that's all we need. Okay, this simulation will take a little bit of time. So I'm going to time the simulation and pause the video and let you know how much time has passed after we see sort of the first couple of steps being taken. So I did produce this video once before and had to delete a fair amount of it because I made a couple mistakes. So maybe some common errors that you might make. You need to make sure you set your phases correctly when you define the method. It's important to make sure you've set those to water and oil. By default, they're both set to air, so your simulation can have some issues with the compressible fluid at the front end if you don't set those properly. But in this case, it looks like we're doing well. So you can see our simulation is churning through, and we're developing our oil at our inlet. It's not perfectly smooth, and this probably reflects a little bit of the fact that our mesh is somewhat coarse relative to the size of the interface. And what's happening is fluid is being injected through the top as well as the bottom, and then all of the fluid is being pushed out the end. So what's going to happen is as this oil droplet, or as this oil jet, impinges into the center of the T, we're going to see the oil sort of pinch off a little bit. And then it's going to go through this neck, where we're going to see an oil droplet pinch off from the jet completely and form an isolated drop. Okay. We can take a look at the residuals while this is stepping forward, and we're doing okay. We don't seem to always be converging, particularly in this area, and certainly now we don't seem to be getting to that 10 to the minus 4. Now we can see the generation of the oil jet, and we can see the process of pinch off for that droplet as it sort of necks and narrows down a little bit. We can see a little bit of fluctuation inside the oil droplet here, but that sort of washes out. And then this neck disappears between the two. The oil's still being pumped in, though, which means we're going to produce another oil droplet. So this red drop is sort of a nice demonstration of the oil that's being produced. So for reference, I haven't paused anything yet, so we are moving along reasonably quickly. This is a little bit faster than I was doing earlier. Again, we're using 4 processors on a VMware machine, so if you are running into issues running this on your local machine in any sort of reasonable amount of time, you might want to consider running it on the VMware, because this looks like it's going to complete without me needing to pause. So we can see the generation of now a second bubble, or a second oil droplet in the chamber, as these are both now moving slowly down. And what you're going to be doing for your homework is you're going to be varying some of the parameters involved. And this is going to result in changing up the generation of these oil droplets. So I'm looking up the homework now while this is running. So for pset 6, what you're going to do is you're going to actually change your time step a little bit and see how this impacts your result. A key thing as you're changing your time step, and I think I saw a couple issues with this in previous Ansys simulations. So our goal is to take the same amount of physical time. We still want to simulate the same amount of physical time. In this case, we have 200 steps of 0.001 time step, which corresponds to 0.2 seconds of simulated time. As you increase your time step from 0.001, you're going to have to decrease the number of time steps you take. Okay? For each of the simulations, you are still going to hold the same number of maximum iterations, and you just keep that at 50 for each one, and see how that changing of the time step impacts the change in your result. Okay, and so we're almost done. We got about 10% more to complete, and we should see we have about 5. We might get a 6th droplet formed over the course of the 0.2 seconds. Okay. So runtime looked like it was somewhere on the order of 5 or 6 minutes. We do see some pretty significant, if you notice, some significant issues with convergence occurring here. So we have 1, 2, 3, 4, 5 droplets have formed, corresponding to sort of these 5 peaks in continuity error issues. And so ideally, you'd be running these simulations, allowing the system to more accurately approach the residual tolerances. That may mean taking smaller time steps, particularly during the pinch-off, which is where these spikes are occurring, or allowing it to take more iterations. Overall, though, we should be pretty pleased with the results in terms of the physics being generated. So we can take a look at the animation, take a look at the playback, and so we've got a couple previous examples that didn't quite work, and then here's our simulation here. So the generation of our first, second, third, fourth, and fifth droplets. Okay, that concludes the second video.